Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. Within this module, we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module, we are currently on the third topic, that is system calls, exceptions, and interrupts. So basically, as you can see, we are nearing the completion of this topic. And in this topic, we discussed the concept of interrupts and different types of interrupts, right? So if you recall, an interrupt is basically a signal that can be generated either from the hardware or the software. This signal is meant to alert or notify the CPU that there exists a event or a situation in the system that needs immediate attention from the operating system. And when the CPU receives this interrupt, it immediately halts whatever it is doing. It immediately halts the current execution of the current user process and transitions the control to the operating system. In response, the operating system executes a special routine in order to deal with this interrupt, right? And as we have seen, there are different types of interrupts. And the three events that you see, system calls, exceptions, and device interrupts, are all different types of interrupts. So, system calls and exceptions are a form of software interrupts, whereas device interrupts are a kind of hardware interrupts. So, this was all that we discussed or studied in this topic in great detail, right? So, in this video, I'll summarize all that we covered in this topic one by one. So, without further ado, let's get started. So we have started this topic with the concept of system calls, right? In the very first video, we introduced what is a system call. So basically, prior to this topic, this is how our understanding of process execution looked like, right? This is a very simplistic model. And as you can see here, basically, the operating system creates the process and then the user process starts executing instructions. So in this simplistic model, the assumption is that between process creation and process termination, all that happens is that the user process executes instructions in the user space, right? But as we discussed in the first video, that this is not the case. During the lifetime of a process, very often the user process will request the operating system to perform certain operations on its behalf, and these operations are performed inside system calls, right? So basically, these are special operations which the user process requests the operating system to do for it, right? And in order to accomplish it, the control is transferred to the operating system, where the operating system executes a system call routine. And once the operation is completed, the control is given back to the user process, right? And we studied in that video that the control alternates between user process and the operating system. So even a simple user process makes a dozen system calls during its lifetime, right? We also took an example of the strace tool to understand that. So this was about system calls, and the very basic definition of system call, you can say it's like it looks like a function call, but it transfers control inside the operating system routine. So you can see here, when we execute the system call, the control is given to the operating system, which executes a special routine. So this was the brief introduction about system calls. In the next video, we took a closer look at what exactly is done inside the system calls. So basically, what kind of operations are performed in system calls. So if you recall, this was the compute stack and this is the hardware layer, right? So in the hardware layer are the physical objects like CPU, memory, the IO devices. These are physical resources. So as we discussed in the first module, we know that the operating system, what it does is that in order to simplify the usage of these physical resources, in order to make the interface easier to use, what the operating system does is that it creates abstractions, and these abstractions are basically virtual resources over these physical resources. So for example, the virtual resource in for the CPU is that of a process, right? The abstraction for the memory is that of address space, and for IO devices it's files and directories. So that is what the operating system does. It introduces, or you can say it exposes virtual resources for the user processes, right? Instead of interacting with the hardware resources, the physical resources directly, the user processes, the user applications will interact with these virtual resources. Now, in order to perform specific operations on on these abstractions, we need system calls. So what the operating system does is that since it's the operating system which creates these abstractions, so only the operating system can perform these operations, right? There are certain operations, like let's take the example of a process. Then you might want to create a process, terminate a process, wait for a process. In case of an address space, basically we want to allocate or deallocate memory. And for files and directories, we have simple operations like opening a file, closing a file, reading or writing data to a file. So all of these operations are basically operations on these abstractions. And the operating system provides this mechanism of system call to let the user applications perform these operations. And as you can imagine, within a given operating system, there are like hundreds of system calls. For every specific operation on an abstraction, the operating system exposes it via a system call. And from the perspective of the user application, it can you can see that the operating system interface looks like a API of system calls. It's like a library, standard library of system calls. So this is how the user application perceives the system call or operating system interface, right? So this was the second video. Then in the third video, we discuss the reason why we need system calls, right? So basically, the concept behind system calls is that the user application is requesting the operating system to perform certain operations on its behalf. So the question that we raised in that video is that why cannot the user applications perform these operations themselves? Why request the operating system? So in that video, we discussed the reasons behind this is that if user applications are allowed to directly use the hardware interface, then there are several problems with it. First of all, it can become very complex, right? And it will be inefficient because operating system deals with the hardware resources in a centralized and efficient manner. It will be non-productive because every programmer will have to write their own routines to deal with the hardware. And finally, dangerous, or we can say unsafe, if we trust the user processes, which we cannot do because we cannot trust the user processes to use the hardware resources in a judicious manner, because the programmers can easily write malicious programs which can monopolize the resources, the hardware resources of the system, and take control over the system. So we cannot allow the user applications to directly interface with the hardware. We looked at several examples in that video of what can go wrong, right? That is why we need the operating system to expose these sensitive operations where the user application is interfacing, basically whether the user application needs some operation on the hardware to be exposed via system calls. The user application cannot or should not be allowed to directly interface with the hardware. It should only happen via the system call mechanism, right? So that was the reason behind this mechanism. And we also compare this with the parent child analogy, right? So if you recall the example, so children are not allowed to perform or do certain tasks because there are certain tasks like driving, cooking, and spending money, which requires a certain sense of responsibility on behalf of the individual, which we cannot really expect from children. So that is why instead of allowing the children to do these operations on their own, they request their parents to do these tasks for them. So this is the concept which is very similar to that of a system call. In case of a system call, the sensitive operations are forbidden for the user process and they request the operating system to do those operations on their behalf, right? So this was the rationale behind having this mechanism. Then we looked at how this mechanism of system calls is implemented, right? So basically we discussed that there is a concept of privilege. There are two types of privilege modes in the computer system. One is the user mode, where the software which is executing in this mode has very limited capabilities. It cannot access all the memory locations, it cannot execute all the instructions. Whereas if you compare this with the kernel mode, in the kernel mode in which the operating system executes, here the software has complete control over the system. It can do whatever it wants. So the idea behind system calls is that when we are performing these sensitive operations, the ones that we perform in system calls, the ones where we basically interface with the hardware, those operations should only be allowed to be performed in the kernel mode. Otherwise, if it is like if some application tries to do it when not in kernel mode, the CPU will raise a error, right? It will forbid the user application to do so. And whenever there is a system call, the user application, first of all, it is supposed to uh, like transition into the operating system. The control has to be given to the operating system, and obviously the privilege level has to be changed from user mode to kernel mode. Once that operation is done, this operation will be done in kernel mode with full privileges. Once it is done, the privileges drop. Like when the user process resumes execution, it will resume execution in the user mode, right? And we also saw that this concept of privilege, in order to implement this mechanism, we need hardware support. Basically, there is a bit in the CPU that indicates the current privilege that we are in, right? So for user mode, we have one value. For kernel mode, we have one value. So there is a bit inside the CPU. And in order to transition between these two privilege modes, we have a pair of instructions. To go from user mode to kernel mode, there is the trap instruction, which is also the instruction to invoke a system call, right? And in order to return from kernel mode to user mode, we have the return from trap instruction. So the point is that in order to implement this concept of privilege, we require support from the hardware, right? So this was about how the system call mechanism is implemented. Then we talked why system calls are not normal functions, right? Although they look very much similar to a function call, right? We took this example of the read system call. Take any system call for that matter. You cannot distinguish by just looking at a system call whether it is a normal function call or not, because they look just like normal function calls. But the point is that, like, why they are not normal functions. First of all, what you see, right, this function call that you see is just a wrapper. This is not the actual invocation of the system calls. We saw in that video that the actual system call is invoked via a trap instruction. So this is the syscall instruction in x86 architecture. And basically there is a assembly code required to invoke the system call, and this piece of assembly code is hidden deep inside the library, right? So there is an agreed upon convention between the operating system and the hardware to basically how should we make the system call. So there will be a trap instruction. The arguments have to be put in specific registers. The exact system call number has to be specified. The result will be returned in specific registers. So all of this is a convention between the software and the hardware. And this instruction is invoked in a piece of assembly code which is hidden in the C library. So this is how the actual invocation of the system call looks like. So what we see is just a wrapper, right? So that function call that you see is not the actual invocation. And finally, we took some time and talked about the overall picture, right? We see that there are so many different type of hardware. When we say hardware, I mean to say the CPU architectures that exist. For example, x86, RISC-V, they have different sets of instructions. We also talked about there is a variety of operating systems. And finally, on top of these operating systems, there are so many choices that we have as a programmer to like which API we can follow. There are so many programming APIs out there. So we talked in that video that how can one write portable code, that is code which is written once can run on multiple platforms, because there are so many nuances, intricacies that are involved for executing a certain piece of code on a certain platform. So we talked about how can we write portable code in that video, right? And finally, after discussing all these concepts about system calls, we looked at the detailed flow of a system call. We covered all of the different steps that are required to make a system calls, each one in detail, right? So at a very high level, you can see the user process is executing. Then it invokes a system call. Basically, it calls the wrapper. It goes into the library, where the library pushes the parameters. It invokes that basically that assembly code that we just saw. There is a trap instruction, which then transfers the control to the operating system. The operating system then handles the trap. It executes the system call routine. And finally, once the requested operation has been performed, the control is returned back to the operating system along with the results of the system call. So we discussed the complete flow step by step in that video, right? So this was about the system calls. So after talking about system calls, then we shifted our attention to the next type of events, that is exceptions, right? So basically, we said that exceptions are errors or unexpected events that are detected by the CPU when executing the current process, right? And when the CPU detects an exception, it immediately transfers control to the operating system, and the operating system immediately needs to deal with this exception. So we discussed that there could be several reasons for exceptions. For example, when a program causes array index out of bounds error, divide by zero error, stack overflow, segmentation fault, page fault, or even when a programmer introduces a breakpoint, all of these can cause an exception, right? So basically, it's an error or an unexpected event which occurs during the process execution. And we saw how the exception is dealt with. When the user process does something wrong, the CPU detects it and immediately transfers control to the operating system. And now the operating system has multiple options in order to deal with the exception. It can either terminate the offending process if the exception is a severe one, or if it is a moderate exception, then it can deal with the exception on its own in a more graceful manner, or it can also allow the user process to deal with the exception on its own. And once the exception has been dealt with, the control is given back to the user space, right? And after discussing what are exceptions, we looked at the detailed flow, just like we did for system calls. This is how the detailed flow of exceptions look like. We have talked about this in that video. Every step we have covered in great detail. So again, the idea remains the same. The user process is executing, it does something wrong. When the CPU detects it, there is a trap, or we can say the control is immediately transferred to the operating system. The operating system handles the trap initially by saving the registers of the user process and then switching to the kernel. Then it executes the exception handler, right? And finally, once the exception has been dealt with, the control is given back to the user process. So the idea is that whatever mistake has happened, whatever error has happened, the operating system has to do take some corrective or preventive action to deal with the exception, so that the overall computer system works in a proper way, right? Then after dealing with exceptions, we talked about the interrupts. So basically, an interrupt, as we saw the definition, it's a signal that can come either from the software or the hardware. And this signal is meant to notify or alert the CPU about an event or a situation which needs immediate attention from the operating system. And when the CPU detects the interrupt, what it does is that it halts whatever it is doing, it halts the execution of the current user process and immediately transfers control to the operating system. And the operating system then deals with the interrupt by executing a special routine, right? So as you can see, interrupts can either be software interrupts or hardware interrupts. Software interrupts are caused by the process user process execution, and events that we discussed just before the concept of interrupts, that is system calls and exceptions, as you can see, are just a type of interrupts. So system calls and exceptions, since they are caused by the user process, when the user process is executing, it's a piece of software, so they are a type of software interrupts. In both the cases, when we make a system call or when there is an exception, the control is immediately transferred to the operating system. The operating system might execute a system call routine or exception handler to deal with the software interrupt, right? So basically, the concept of interrupts is a more general one. System calls and exceptions are a specific type of interrupts. And apart from software interrupts, we also discussed that there are hardware interrupts, which are caused by hardware devices like the IO devices, the other hardware components on the computer chip, right? So these are basically device interrupts, and a major source of device interrupts is the IO devices. So there we discussed the concept of interrupt-driven IO. So in an interrupt-driven IO, basically it is initiated by the user process. It basically initiates some kind of IO operation, as you can see via a system call. Once the IO operation is initiated by the operating system, it goes on in parallel along. And what also the operating system does is that after initiating the IO operation, it switches back the control to the user process. So the user process to some other user process. So that user process and the IO operation go on in parallel. So computation and IO operation go on in parallel. And once the operation is complete, the device interrupts the CPU, and the CPU then immediately transitions the control to the operating system. The operating system then deals with the interrupt. So this is interrupt driven IO, where the IO operation utilizes the mechanism of interrupts, and they are a major source of hardware interrupts. So we discussed that device interrupts can be of two types depending on their nature. One can be expected, as is the case for interrupt driven IO, where the interrupt that is coming is kind of expected. The user process was the one who had initiated the IO operation, and once the operation is complete, when the interrupt comes, it is kind of expected. We also discussed that there could be some random type of device interrupts which are not kind of expected. For example, the battery going down, or the CPU temperature going high, or new input arriving suddenly, right? So all of these are random device interrupts because they can arrive at any given point in time. Their occurrence is random. And finally, we discussed the difference between hardware and software interrupts in that video. So this was about interrupts. Then we looked at the detailed flow of interrupts. So the flow is again very similar, just like system calls, exceptions. Device interrupts also have a similar flow. We discussed the each of the steps in great detail in that video. We also touched upon the overall interrupt hardware that exists in the system. There is an interrupt controller, which is like a centralized chip for overall interrupt management in the system. We saw how a device can raise an interrupt, how the CPU can detect the interrupt by sensing the different lines on the bus, right? So this was about the interrupt hardware that we saw. And finally, we also looked at the concept of interrupt vector table that resides in the memory. Basically, when the operating system boots up, it locates all of the interrupt service routines that are there for different devices and puts their addresses in the interrupt vector table. So whenever there is an interrupt, this table can be accessed to quickly get the address of the special routine or the interrupt service routine that needs to be executed in order to deal with the current interrupt. So this was the concept of interrupt vector table. So this was about interrupts. In the final video of this topic, we looked at the x86 operating system and discuss how interrupts are dealt with in the x86 operating system, right? So basically, in x86, all of the different types of interrupts, whether software or hardware interrupts, they are given a common term, that is traps. So system calls, exceptions, and device interrupts, all of them are given the common terminology, that is traps. Basically, you can think of them as interrupts, right? And we looked at the overall flow of how traps are handled in the x86 operating system, because till now we had just talked in a very generic on a very general level, right? So there in that video, we looked at the code flow of xv6 and how each of the different types of traps is handled using a common flow, right? So we discussed all of the steps in great detail in that video, right? And finally, there we talked about a very important concept that whichever type of trap it is, whether it is a system call, exception, or device interrupt, in xv6 at least, all of these are handled in a similar way. All of the traps are handled in a similar way. And the most important part in handling the trap is the transition between the user process and the kernel. Understanding the transition gives you an idea of how the traps are handled, right? And like for making the transition, what happens is that there are a certain set of information, there are certain values, or you can say certain registers. If you know the values of those registers, then you can accurately describe the execution of the user process or the kernel. So we discussed that program counter, stack pointer, address space pointer, and the general purpose registers. All of these, if you have all of these information, if you have, then you can accurately describe the execution of the user process, the current state of execution. The same is true for the kernel. In that video, we also looked at how the kernel address space looks like. And finally, coming back to the transition, so making the transition between the user process and the kernel is a matter of switching these important registers, since these set of registers can describe the current state of execution. So in order to transition from one to another, we just have to switch these registers. So we saw in that video how that switch takes place, like going from the user process to the kernel and coming back from the kernel to the user process is a matter of switching registers. So that we discussed in that video, right? So we looked at a real example, that is the xv6, that is how traps or interrupts are processed there, right? So guys, this was a brief summary of all the different topics that we touched upon in this topic, right? So this topic is now over. In this topic, we discussed about the concept of interrupt, different types of interrupts, system calls, exceptions, device interrupts. We also looked at a real operating system, that is the xv6, and saw how traps or interrupts are handled there. So basically, the point is that any operating system heavily leverages this concept of interrupts during its working, during its execution. So there are several important events like interrupts from hardware devices, uh, errors made by software, so that is exceptions, or even when user processes require the attention of the operating system. So there are many events that require the immediate attention of the operating system. And in order to have this mechanism in place where the operating system's attention can be drawn, we have the concept of interrupts. So it can either come from software, it can either come from hardware. In any case, interrupts help the operating system to deal with the most or immediately whatever is important. To pay attention to that is what the interrupts enables the operating system to do. So this was about interrupts. Now from the next video onwards, we will start with a new topic, that is we will discuss the system call API for processes, right? So we will go over the different system calls, real world system calls that are available in the Unix operating system that allow us to deal with different aspects of a process, like process creation, termination. So overall process management and the related system calls we will study in that topic. So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.